All right, 7 o'clock. Let's get started. Today is on review number lecture 5. For the last few reviews, or for the last few lectures, you have learned how to play with either you have to about solving problem, and we talked about time and space complexity. And for this lecture 5, we wanted to talk about debugging and the rest. So actually. So once you know how to program, the next thing is that you need to debug. And are you sure it is correct? So that it's always the aim of this. But as you learned in the last week, that it got to do with the objective and the assumptions that we said a particular program is correct or not. All right. But of course, no matter how hard you do, most of the time the testing is to certain limit only because in the normal case with a program of many branches, there is going to be lots of things that you have to test, and you got no choice but to be selective in certain manner and based on your judgment and to make good as much as you can. So for today, we are going to do just go through pretty much this lecture, and I find this lecture kind of interesting. It's a compilation of our experiences in here, and but still, I should at least say more than that. And I wanted to do this review, and in the second half, I'm going to show you something. To me, it's kind of interesting to discover with the use of Python Tutor to see how you can analyze your program. Right, and I have already posted a question in the forum, and one of you, yesterday's group, has answered it in certain manner. But of course, it doesn't stop you from also trying. Okay, for review lecture 5 on debugging, so time and space. All right, so we are dealing with just Python. So as you will learn from your tutor, there are certain things peculiar or specific, all right, to Python, and you have to then use it. For example, I attended yesterday's tutorial by a TA. There was this issue about range. Actually, range is an object, and the object as such, once it is defined, you cannot change it. And no matter what you change about the I, that it's part of the range definition. Subsequently, the I changes doesn't affect the range actually. All right, and we are dealing with just Python, but about dealing with other things like in the picture libraries that you encounter, there are specific things about the libraries. Of course, it's not just about picture library. In Python, it actually why so popular also because it has support to many libraries are based on Python. And then you write codes based on Python with them. And of course, you need to know their characteristics to then know where could possibly be the troubles in your code. All right. So for today, for us, or in this course, we don't deal much with other libraries. We are just simple library like mathematics. Of course, there's not much to talk about. You just call a function. Not unlike some other libraries where you have to call actually you have to set the stage, then you can then use it and so on. So there will be multiple statements to be able to then use that particular library. For those cases, there will be peculiarity or characteristics that you would have to follow to then get the library to work. All right, so there are a few points I wanted to go through here, and then we talk about the other thing. Okay, first of all, tracing is a particular tool that you have to learn, and many of the past year exam assessments you will see got codes for you to try to figure out what are the answers, and those things are using you don't have you don't have a computer with you, you just have the uh, pen and pencil, and you have to draw a lot of pictures to show how things work. The debugging, as you learn in that in this lecture, it's about understanding the flow of the code, right? Right? Is verifying the flow and the values. All right, tracing it's meant for that purpose. All right, and once you know that, with small example as always, you don't expect yourself to do this kind of tracing with huge number or huge example. Our purpose is that to trace small example to then understand its semantics. Then you can deduce what would it mean by bigger examples. Okay, so the tracing usually means it takes a small example to minimize the use of the time and then to figure out what is the semantic, then you can then deduce what it means by bigger example input without having to trace it anymore. All right. As you know that last week I mentioned that debugging actually take a long time. So tracing is a kind of ways that you have to then help in your debugging of your code. Right. So by now you should be not from you should be very familiar with it because you've done quite a number of programs now. All right. So in this lecture, I actually listed quite a bit of user mistakes. Some of these are pretty low class in the sense that you shouldn't make them. All right. And but of course, there are examples which are unavoidable, and you got no choice but to trace it. Here are a few things that I can say about common bugs or common mistakes that we make. In the sense that myself is also committed also commit to such kind of mistakes too. For example, sometimes we mistaken the percentage with the integer divide. Integer divide is to get you the values of the division, whereas this percentage is just to get the remainder of the divisions. Right? So we may at time forget about this. And the next thing is that currently what you're dealing with before you deal with other data structures like list, dictionary, set, and so on, you already probably encountered tuple and string. All right, strings, as you know, strings means things like this: A, B, C, D is a string, right? So you have this, and you can say things like string number 3, the third character, the third from the left is 0, 1, 2, 3. So this should give you the D. Okay. And if you deal with, instead of the third, the fourth, which is no longer in here, then you get an error because it's out of range. On the other hand, if you are dealing with this, which you say starting from 4 onward, then you don't get an error, but you get an empty string. This is the same as for the tuple, an A, a B, a C, and a D. All right, this is a tuple. The tuple, if you want the third guy, in this case, which is a 0, 1, 2, 3, which is the D, you get the D. If you want to get the fourth guy, there's no such thing as the fourth guy here because it's only 0, 1, 2, 3. You will get an error. And there was a question that do I need to know why this error in answering to some of the assessment question? No, you don't have to. You just need to know that there's an error. Okay, if you're asked to trace what this is. On the other hand, it's the same as before. If you start from fourth onward and you get an empty tuple, without any error. Okay, so this kind of characteristics is used in our recursion. As for example, we have the recursion that here. This is a reverse recursion. This is a Python tutor. By now you should know. So this is a reverse function. If the tuple is empty, then you return the empty tuple. Otherwise, you return the last guy. All right, you need to comma it. Without a comma, you will not get a tuple. You will just get the last character, which is wrong. So you get the last guy in the first round, it will be E. Then you reverse apply the recursion starting from beginning to before the last guy, which means from A to D. So it looks like this. So you have this uh, tracing to see. All right, at the end of it, the return value is an empty thing. All right, and then you reverse back and you get EDCBA. Okay, so this is your answer. All right, so this is talking about tuple and use of tuple with in the recursion. And because we use until, so this is either a string. So for example, here in this case, if you say this until the very last guy, you actually get A, B, C without the D. Okay. All right. So one thing to note here as a side note is that string and tuple, they behave the same. All right. If string can give you error, most likely the tuple or the same operation on tuple will be error. So here I listed sequential statement can have prompt, conditional statement can have prompt, and recursion can have prompt, or looping can have prompt. So for the case of conditional statement, we saw this 3 to the power of 4 to the power of 5. And because of the either the left or the right associativity, you could have 3 raised to the power of 4 raised to the power of 5 first, or 3 raised to the power of 4, then raised to the power of 5. So which is which? In this case, it is a right associativity. So the 4 to the power of 5 first, then the answer here will be used to raise to the power for 3. Okay, so this kind of code, of course, is meant to test you, but it's not meant for people to read because you know the intention. So if you want it to be this way, it's best that you actually pick the parentheses explicitly. All right, so always remember this statement. We write program not for us to read only. We also meant for other people to concur or to verify what we have written. Okay. On the other hand, also, if in other situation, if statement you have seen before, be careful if you are going to do comparison with floating point number, and some of this floating point number may not be exact, and there will be unexpected result if you try to compare exactly. Okay, so be careful not to use it. All right, as for looping, so the iterative and recursion, as in the last lecture, and there are various for the recursion. We know that we must have base cases or base case, and we must have smaller examples, smaller problem when we call the recursion. So like here, this is a recursive call, and this problem is smaller because it has one less element in the tuple to be calling the function. So you are getting a smaller number. And here's the base case. All right. So it has to have these two. And there's another property about recursion that we will talk about it. Basically bringing the baggage with you into the recursion. Okay, I will give some examples of that. You can see some of this in the assessment also. All right, that is about recursion. As for iterative, and here's an example of iterations that could be interesting. Here, this is the code, right? It's quite common in the tracing exercise. So like here, of course, this is more tracing than finding bugs, but still, it also indicates the boundary condition. So for example, you have a loop, j equal to 0, which is counting the number of times it goes through the loop. So you want to return j, which is the number of times this loop is being executed. And this loop is started with 2 and ended before 100 and at the increment of 3. So for that, you know that this means that this is starting with 2, then add 3 become 5, add 3 become 8, until who is the last guy? The last guy has to be a number smaller than 99, but 99 is modular 3 equal to 0. As you can see, 2 is modular 3 equal to 2, 5 modulo 3 is also 2. 8 modulo 3 is also 2. So the last number here should be modulo 2. So if it is not 99, because 99 is modulo 0, 3 equal to 0. Then 98 is exactly modulo 3 equal to 2. So the last number is indeed 98. All right, if you don't believe it, we can see print I. And we visualize it. Right, 98 is the last number. Okay, so it is it's not that we printed it out to see the number, but by our deduction that we know that the last number is 98. It cannot be 100, it has to be before 100, so at most it's 99, but 99 is modulo 2, modulo 3 equal to 0, right? It's fully divisible by 3. So 98 is the one that you divided, you get exactly remainder of 2. Okay, so what is the output of J? As you saw just now, it's 33. Why is it 33? So if you need to analyze it by hand, then if you do not know this is 1. You can map 3, 2 it become 1, 4 become 4, 8 becomes 7. So the last number is 97. All right, so from 1, 4, 7 until 97, how many of them are there? So it is quite easy. It's that you just take 97 minus 1. All right. Just like if you have 1, 2, 3, 4, 5 until 100, how many numbers are there? It's 100 minus 1, which is 99 plus 1. Okay, so this is what it is. In this case, we need to divide by 3 because it's increment by 3. So this is equal to 33. All right, this is 32 plus 1 is 33. So we can see. All right, so J is 33. Okay, so this is how you can figure out the boundary condition. All right, and then to know that whether whatever you written here, it's indeed what you wanted. All right, you wanted 33 times in this case. Okay. All right. So other than tracing, finding these are the common bugs. What do we usually do to get to trace is as I have done it just now, which is the printing of the statement. I use the print I here, and I cannot, I must emphasize this over and over again. We do more than just a print statement because print statement can be very ugly. And of course, there's way to hide the printing by doing some status thing. But on the other hand, it's more than that, that sometimes we write extra function or functions to help us to make sense of things or to do the automated testing. And the next point is Python Tutor. It's a very good tool as you saw here, and you also saw here in this case. All right, you see that the execution, it's there, and not just tracing it one by one, line by line, which is you will have to do during assessment in midterm or final exam. It does give you all the pictorial view of things, right? You see that this is in fact a data structure. This is another data structure, data structure, data structure. It also depicts that how you get all the structure, the data that you needed. In this case, the data that you needed is tuple of length 1, tuple of length 2, tuple of length 3, and so on until tuple of length n. And therefore, this is 1 plus 2 plus 3 plus 4. So that the storage itself is already n squared, all right? Because n is the length of the input tuple. And because you created many other guys, each time you create it, you need to pay for it. From n to become n minus 1, you pay for the time. Okay, so this is one form of you see the picture. And last week, when we talk about we had the table, which is the common one. If you are iterative solution, you have the table to help you to do the tracing. Right, I did it with I equal to 1, product equal to 1 and time 1. product I equal to 1, and when time 2 and product become 1 and so on. I did that for you. All right, so this is a table to do the tracing. Other than these are the data structure. And this is the other way I did tracing to show you explicitly. And this one is that there are 5 defer operators of the multiplications. So the space that you have is exactly the size, the number n. So the space is O of n also. And the time in this case is O of n. So all right, so this is another form. So basically, you invent different kind of tables or charts to help you to do. Here is another one. This is from lecture 8. This is a tree structure. All right, a tree is a tuple of tuples or sequence of sequence or sequence of sequences. And this is the kind of picture you have to draw to help yourself to understand the codes. Okay, so in various ways, you have using different kind of drawing, all right, to help yourself to understand your code. Okay. And the second point I had was the space. All right, for the space, here it's just two statements to tell you that last week we saw this thing. This is how we have 5 defer star, so the storage needed is O of 5, or actually it's O of n because 5 is the input, right? All right, so here you saw the space as in horizontally. And in Python Tutor, you actually see like that. It seems to be vertically, but in fact, all these things are stacked on top of each other. It's as if you have it in one line here. All right, so this is a picture of one line. Because I can draw it, I can say in one line here because these are stars. Whereas this one, I cannot put everything in one line. Of the drawing in this manner is more clearer. It's less ambiguous. So it's actually, this looks as if it is vertical, but actually it's the same as this guy. You should list all these things one after another next to each other in the system storage. All right, so this is the space. All right, so in the Python tutor, you're actually seeing it seems to be vertical, but it's not vertical. All right, so and let me use the word footprint again. So this is the footprint. The space complexity is actually the largest size of the footprint. One thing to note is that time is it's like money. When it's spent, it's spent. All right. On the other hand, space, if it's spent, at time it can recover because it can recover, but we're only interested in the storage. For example, you see here, uh, if you continue doing it, all right, you see the space is recovered. All right, but we always take note that when was the point that you use the most amount of storage, that will be the space complexity. So that you cannot claim that the space complexity here is linear. Okay, for this instance, it's linear, but not to forget that before that, you have it, all these things stack up. All right, so we take among all the time steps, the one with the most amount of space used as the footprint. And that footprint is your space usage. I think you can do the same for this last recitation number 2. We have the n squared time and the order n space. You can see that, all right, it is the factorial that is using the space factorial. Oh, maybe this is too big a number. Let's use 5. Okay, so you see the factorial is the one that using the space. All right, now you go to the factorial. Oh, actually, this guy also stack up. So there are 2 places with the space that you are using. Oh, on the other hand, this factorial is actually iterative. All right, factorial is iterative, so the space is O of n1, constant. All right, unlike the next one, which is the this one. This one is the recursive version. Let's see this one. You see? All right, you have the find e when n equal to 4 and factorial, you have to find 4, factorial 3, factorial 2. All right, so the not just the factorial find e has the linear space needed, the factorial also linear, but the two linear added together is still linear. Okay, you see that it never got, unlike the case of what you saw with this guy, this is linear here, linear or linear minus 1, linear minus 2, and so on. So this added up to be n squared. Okay, so the sum of the tuplets is the space that we use, and this is a footprint of memory we use. Okay, I'm pretty much done with 1 and 2. Any question? Or give me a check. I can then move on to the next part, which is more interesting. Yeah, okay? Okay. The interesting thing is here. So we said that last week that this is n squared time and space O of n. The space you can see clearly. Okay, what about the time? How do I know that this is indeed O of n squared? Of course, by training, by now, you should know how to analyze this thing and you can get this. But actually, Python Tutor, here I can show you something which at least we should do it once yourself and to convince yourself that this is actually n squared. So I'm trying various examples. Here I have a spreadsheet. Let me show you the spreadsheet. Okay, this is a spreadsheet. I have this find E recursion. I wanted to charge up this guy. This is the time for this recursion. All right, you see. So let's run it to the last. You get the answer here. This is when you find E5. You use 72 steps. How does this 72 step come about? You do it one by one like that. All right, you indeed. Okay, every step may be different in time, noted, because some of it is simple or it's a simple check. But we know that plus, minus versus divisions and multiplications, they are of different time, but the time difference are all in constant multipler. So we treat all of them the same. So the 72 steps, we treat them all the same amount of time. So we can fill in for input n equal to 5, we can n equal to 5, we have 72 steps. Okay. And you can do the same for 25, for example. Opt, this Python tutor needed more space and this is not enough. So I cannot get anything. So this is cross out. I knew that 24 is the one that I can still get with this Python tutor. Okay, I get 775 steps. All right, plus this is your answer. It does use 775 steps to get the answer. So this step is all right, 775. Maybe use a white color is easier to see. Okay, and this is 72. Okay, likewise, you can do it for the rest. Let's say 12, which you saw just now. All right, 247. 12, this is 247. Okay, and you can do it for all the rest. Okay, here are all your number. Maybe black color is easier. Okay. All right, so these numbers are charged out like this. So for example, 12 is here, 247. 24 is here, 775. So this curve. So how do we know that this curve is actually n squared, as we claim here, n squared? So to know n squared is to know the growth. All right, the growth means you want to know the gradient of this guy. This gradient, you know that n squared. When you take the gradient, you mean the slope. You should get linear. All right, so let's see. So This is the time t minus time t minus 1. So this guy is time t is n equal to 0, you got 7 steps. N equal to 1, you got 16 steps. So 16 minus 7, you got 9 steps. 27 minus 16, it's 11 steps. Okay, this is 9 divided by the magnitude of the length, the x. This is the y divided by the x. The x is 2 minus 1, which is 1. So this is slope. This is 9. This is 11. And this is 40 minus 27. This gives you 13. So by the same manner, you will get all the rest. So this is the rest. And we can see it here, the growth. Okay. So the growth is here. Look. So this is pretty straight here. So let's try. Dylan. Hi, Dylan. Are you there? No. Isaac. Isaac Tam.
Yes, Prof.
Hi. So what do you see here?
Linear growth, Prof.
Linear growth. How do we know
Yes.
it's linear? So we can try it out, right?
Yes.
Let's see. So if you know this is linear function that its gradient is linear, so this guy is n squared. So let's get the n squared in place. So n squared. So 0 to the square is still 0, 1 to the square is still 1, 2 to the square is 4, right? So this is the what you get. So these are the number. So for example, 24 square, it's 576, right? Square. Okay. So how does this look like? You can see the curve. N square. You see here. So Isaac, what do you see? So this guy is pretty much below this orange guy is below the blue guy, right?
Yes.
Ah, so but they look similar,
The same.
huh?
Yes.
Yeah. So this guy is actually describing the slope, and but it's below. But what we want is on top, right? So we can try something on top. So we can try, for example, let me uh take this time minus away n squared. So this should be time. I get I get all these number. So all these are positive numbers. So it means that the time is on top of him. Okay, so here what we are showing only from 0 to 24. By right, you should do this thing 0 to much bigger number to then ascertain the fact that this is in this shape, huh? But because of the limitation of this Python tutor, this is good enough for illustration. In actual fact, you could have run the program doing some counting yourself. There are tools like that around. So this is now, but this guy is below. I want it to be on top. So I multiply with the 2. So I take 1 multiplied by 2, I get 2. 4 multiplied by 2, I got 8. 9 multiplied by 2, I got 18, and so on. So this is what I have. Okay. And now if I take the difference of the two guys, I take the time minus this, I see that, maybe I show the curve first. Multiply by 2, huh? So here. Now you see this gray color thing. At some point, it crosses the blue and go on top. All right. And now you see this is indeed what we talked about last week. All right. We wanted to find the k and the n0. So this is a natural choice of n0 here. Anything larger than this will do. And the k here means the k that we choose for our constant. In this case, I chose k equal to 2 to be on top here. All right, so let's let's move this a little bit. Let's see it here. So I take the time again. This time minus away the 2 to get the some positive. So here are positive. These are, oh, did I change some number? Okay. These are positive number. And then it switched to negative, right? Meaning that 2n squared is now larger than the time. All right, so it's on top. So here, actually, what you're seeing is, let me just copy this. Maybe they are here already. Yeah, here. All right, so k equal to 2, n0 equal to 9. At 9 here, all right, is 9. You already get negative. All right, so when I choose k equal to 2, n0 equal to 9, I can ascertain now that following the definition of what we learned last week, I have the function time is indeed O of n squared. Correct, Isaac?
Yes.
Yeah, okay.
Yeah.
Okay. So let me see. All right. Then next. So actually, also if you follow last week, if you follow the theta, you need to K1 and K2 and N0. For theta, you need to choose three numbers. All right, the K1 and the K2 to bound the Fn. Our Fn is this time is Fn. Our Gn is this guy. Okay, and it tells you that you want to find K1 and K2 multiplied to Gn so that the function, the time is between the two guys. In this case, if you choose K equal to K1 equal to 1, K2 equal to 2, and indeed the Fn is indeed equal to O of Gn, theta of Gn. Okay? Is that okay for you, Isaac? At least I can check with you first.
Yes.
Okay. Now, so we have ascertained that our function Fn, as what we started off to do, to establish that it is O of n squared, and that the space y you saw in the animation here. All right, so, and indeed, we established that this guy is theta Gn. All right, more than this, we talked about also last week, if a function is Gn, all right, if Fn is equal to O of n squared, then the function is also O of, okay, this is also less than or equal to function of O of n to the cube, for example, all right, or n to the 100. But we don't like all these things, okay, because this is not going to be tight. We want something which sandwich whatever function we have as close as possible, as much as we can understand. By putting n to the cube means that you don't understand, all right, because this is way off. Why this is way off? You can see it here. Okay, let's see. This is of course, here's another line to show you. This is if a function is 2n, it works, then 3n also work. Oh, sorry, 3n squared also work. All right, so that means that the k that you chose instead of 2, you can choose k equal to 3 and it still work. All right, so this is just this column. Let me move this around. Oh, need to move this. Okay, here is the n cube. It's this. Oh, yeah. All right. N cube will be, take n equal to 1 is 1. N equal to 2, why is it 8? 3. Oh, n equal to 2 is 8. N equal to 1 is 1. This guy is 0. Okay. And so on. So n cube, if you take n cube, you take the time minus n cube, right? You will get this. I don't have a number here. So this should be equal to time is here minus the n cube here. You see, very soon you get all the negative, which means that n cube is on top of him. Let's see. All right, you see, this guy is on top of all the rest now. This is n cube. Okay, so it means that you have a function which is O of n squared. It can also be bounded by O of n cube. But of course, we don't like this. I better disable this because you can't see the rest anymore. Okay, any question? You're okay with this? Give me a check if you're okay. I have a little bit more to go. Okay. A little bit more. It's last week. The last part is to ask you to write an iterative version of this. I intentionally didn't give it to you. Here is the answer. All right, this is in recitation number 2, question number 7. This question. You could have written it in this manner. So this is the code. You can make everything in here and bake your factorial calculation in here as well. And if you do that, we see factorial find E5. Let's see. What's the answer? The answer is 2.71, no difference from the before. I did the code. 24. 2.718, which is correct. So this code is correct, of course, by examples, which is not supposed to be the case. You have to debug and so on. But trust me, okay, so now with E24, how many steps? 81 steps. So it means that, where's my spreadsheet? All right, so here it is, 81 steps. All right, and you can do the same for the rest. I did the code 12. 45 steps. So 12. This is 45 steps. Okay, so and so on. So you can get all the rest. All right, let me just lower down the color. Okay, so you can see. All right, so this is the time for a new function f prime n, the time with these new codes that you have, that I have. And here is the time. So we want to analyze this. Again, you go through the same thing. You find the delta. Delta means the difference. 12 minus 6, you get 6. 15 minus 12, you get 3. 18 minus 15, you get all the rest. They are all 3. You can see constant. So this is a function. When you differentiate, you get constant. A function has to be linear, then the differentiation will be a constant. But if you don't believe, let's take a look. Oh, I need to minus away the best. The time, all right, so this is the, what have it? The best time, yes. Okay, so, and this curve, okay, which is here. This one, next one. Here, this one, the one in the blue, the dark blue. Okay, so this one. So this guy is shown here and you want to see that you want to define the function. Again, you do the same thing. You choose a constant. In this case, I know that it's 3. So I choose a function n plus 3 times 3 equal to 3n plus 9. So basically I choose my k equal to 3 to 4. Okay. And I got this function. And 3n plus 9, as you know, and last week, 3n plus 9 is less than 3n plus n. And 3n plus n is actually 4n. And if you use 4n, you will get these numbers, right? 4n. When n is 1, you get 4. When n is 2, you get 8, and so on. Then if you take this function, which is this column, right, minus which is 4n, you will get all these numbers. So what are these numbers? You can see that there's a 0, they're decreasing until it's all negative, which means that the function 4n, it's on top of this fn. All right, and therefore we have succeeded in getting our function defined with k equal to 4 and n0 equal to, which is here, equal to 9. All right, or you can choose 10, doesn't matter. All right, so these are what we have. That with graph, you can actually see you choose k equal to 4 and n0 equal to 9, and we use 4n. We have defined that my f prime n, which is my better algorithm, is equal to O of n to calculate the Euler's number. All right, so I'm done with this charting, and you should try out. I've already posted in the forum, and someone has answered it, but you can still try it yourself. Okay, so I posted it, and one guy has answered it, but you should try it before you look at the answer. Okay, I'm done. Any question? You okay? All right, of course, this is only an exercise during our free time. You won't be asking to play with spreadsheet in any of the assessments. All right, this is just to really ascertain what we talk about in theory, and then here is in practice. In practice, indeed, you actually can use tools like this to find out the number of steps. All right, if you want to. Okay, I want to here because I wanted to show you that how do we derive n squared for our first attempt, and then we get linear for our better attempt. And there was a question yesterday also, when you present your solutions to any question, if it's not the best, would you get credit for that? Yes and no. Yes, in the sense that if the question doesn't explicitly spell out that you must get me the best, then you will get credit whatever answer that you give meet the objective and the assumptions. On the other hand, if the question asks you for the best, then you would have to give you the best. Okay. Uh, by the way, here I have a few more tabs to show you that you can try it out yourself. This is n square O space. The code here, you know that you can swap these two guys, right? By swapping it, would it make any difference? You can try it out. And also, we saw this factorial. If we use recursion, the number of steps is going to be different, but would it change the complexity of this code or not? All right, so you can figure it out with the chart also. And of course, you can, as I put it in my question, there are two ways to do it. You can do careful analysis and tracing, or you can use the Python tutor to, you can use a Python tutor to do the graphing. Okay, I'm done with this. If you're okay, give me a check. Okay, let me see. Junjie is here or not? He's not here. Another minute is to Hmm? Junjie, are you here? Oops, don't tell me you forget. Let me call him. Okay, let me stop the recording. Oh, Paul, can you? Okay, great. So I'll mute myself and uh,
Okay, guys, I'll start the tutorial at 8. Feel free to take a break.
Junjie, you are muted.
Oh yeah, I need to set up a bit.
Okay. Yeah, you can start, right?
Yep. Right, hi guys, I'm gonna start the tutorial. Right, okay. For question 1, we will define a function magnitude that takes in the coordinates of 2 points on a plane. And you have to return the magnitude of the vector between them. So what this question applies is these two map formulas. So first you have the formula to get the vector between 2 points, and the formula for getting the magnitude of a vector. So you all might have learned these formulas during A levels or O levels or poly, but we'll be applying them in this function. So can I see your answers? I just paste them in the chat. All right, thanks for your answers. Jonas, can you explain your answer? Jonas Chen?
Hi, can you hear me?
Yes.
Okay, so it's just firstly is to find the length, which is using the x coordinates. So you take like start minus n or x1 minus x2. Then you apply the same to the height also, which is then y1 minus y2. Then to find vector, it's the square root of the height power 2 plus length power 2, in this case to give you magnitude.
Right, thanks. So yep, everybody basically did it the same way. So you applied the two formulas one way or another, and you return the square root or the powers of the height and the length to return the magnitude of the vector. All right, let's see if anybody did not use the math library. Right, I see some ways. Basically, you'll just apply the power of half. So that's the same way. You don't actually have to import the square root function. All right, everybody basically did it the same way. Okay, let's move on. So for question 2. Question 2, 2A, you have to find the area of a triangle using the half times base times height method. So let's see your answers. So far it's a very simple question so far. So the formula has to take in two inputs, base and height, and return the area of a triangle. It's good for you guys to look through everybody's answers so you can see any alternative ways of doing things. Right now, the questions are still quite simple, but down the line, we'll get like more complicated questions and there will be like many different ways of solving them. So it's good to be able to understand all the different ways. But so far, yep. So basically, it's very simple. You apply the formula, you take in the two inputs that vary, base and height, and you apply the mathematical formula to return the area of a triangle. Yep. Okay, for question 2B, so this is just a different way of calculating the area of a triangle. So you apply the formula half times AB times sine AB. So it's just different inputs. So can I see your answers for 2B? All right. There's basically only one way to do it. So you apply the formula half times A times B times sine angle. Okay, for 2C, okay, I'll ask the Bansha, can you answer 2C? Both functions calculate the same result. Can they be directly substituted for each other?
No, because the first function only takes in it only takes in the base and the height, but the second function takes in a, b as well as the angle. So there's an additional parameter.
Right, different number of variables. Any other points to add? Like you can add to the chat. Anybody has anything to add? Right, I see some answers. So basically, yeah, you cannot directly substitute them. Not only is it because they take a different number of variables, like if you were to pass in like the same two variables for area 2 to the area 1 function, it's not going to work because like area 1, if you pass in the same inputs, you're going to get a type error because like area is only defined to take two positional arguments. So if you give any extra arguments, it's not going to be accepted. Same thing as if you try to call area 2 with area 1's functions, with area 2's inputs. This is also going to get error. This will also get a type error because area 2 needs 3 arguments, while area is only defined to take. No, area 2 takes 3 arguments and you only gave it 2. But not only because of that, it's because the two functions are also coded differently. They use a different line of logic. Like area 2 applies this formula, area 1 applies a different formula. So even if, let's say, you use a right angle triangle that technically could use both formulas, but if you don't give in the angle, like the function is not going to work correctly. All right, for 2D, so here's another function, another way of calculating the area of a triangle using Heron's formula. So Heron's formula has been given to you already. So write a function area 3 that uses Heron's formula to calculate and return the area of a triangle. Can I see your answers? All right, Kurt Hippolito rebellion. Can you explain the answer?
Sorry, I didn't catch that.
Can you explain the answer?
So firstly, we need to find the three magnitudes, which is A, B, and C, right? So the first length is the first coordinate and the second coordinate. The second length is the magnitude of the first coordinate and third coordinate. Then the third length is the magnitude of the second coordinate and third coordinate. Then you return the result for uh the three lengths and then put it into the Heron's formula function, which basically inputs the formula there. Yeah.
Yep, thanks. So yeah, so you just save the three lengths of the triangle and you apply Heron's formula. Because Heron's formula is a helper function that takes the three lengths. So first you have to calculate the three lengths using the input points. Then you can get the area of a triangle. All right, let's see the other answers. All right, most of you did it the same way. I'll just show a different way also. So I saw somebody did this way yesterday, where they did it like they did it like that. Okay, so let's get Elgar Seng Hao Yu. Will this way work?
Yeah, hello. Hello.
Hi.
Return Heron's formula magnet. I think, yeah, I think it will still work.
Let's see.
Oh,
Oh, I need to go and define magnitude. Yes, it will still work, but would this be a better solution compared to this? Like, can you comment about it?
this one is like less readable. It's quite long. And the one above is like understandable. Like length one is you just use the magnitude function for the four variables. And
Yes,
so
thank you. So yeah, so this way is better because like you can see anybody reading your code or you yourself reading your code later in the future will be able to understand what the saved variables refer to. Especially when you use descriptive names for your variables. It's generally a good thing to write your code like this, so it's more readable in the future. If you push everything in one line and it gets very long, it's also very difficult to read, especially when you nest like different function calls, like you nest a lot of calls to magnitude inside the call to Heron's formula. So it's not immediately obvious what you're doing when you're looking at this one line, whereas when you're looking through this one function, it's better. Now, what about the space complexity of these two functions? Let's see, Qishen Li. Is there a difference between the space complexities for these two functions?
Hello, can you hear me?
Hello?
Yeah, okay. I think there is.
Okay, so what is the space complexity of this solution?
Sorry, not quite too sure about this.
It's fine. Okay, can anybody else answer what is the space complexity of area tree? Isaac Tam?
Hello. Can you hear
Hello.
me?
Yes. So what's the space complexity of this solution?
Let me think. 01 constant.
Okay, why?
My all deals with simple multiplication and then subtraction. So yeah.
Yes. But basically, when we talk about space complexity, we talk about how big of a thing that we are storing. So all these are constants, right? Constant
Yes.
variables. So no matter how big the input scales or like how big these numbers get, we are still keeping track the values of three constants. So no matter how the input size changes, the amount of space we keep is constant at three variables. So that's why space is O1, constant space. Now the same thing is true for here. So over here, you don't save any variables, but still, like, no matter how the input changes, we use the same amount of space, which is O1. So both of these functions use the same space complexity. Okay. Let's move on to question 3. Okay, so question 3 is a code tracing question. We have a lot of different expressions. So this is a common theme that will come out in exam. So it's basically a code tracing. You're supposed to look at expression and evaluate it yourself without the help of a Python terminal. So I'll get like some of you guys to try and trace through the functions yourself. So Yung Feng Li, what is the output to full one? This called full one.
45.
All right. Can you explain how you trace the result?
Just every I from 0 to 9, 0 plus 1 plus 2 plus until 9.
Yep. Okay. So if you don't understand how to trace a function, you can use this helpful tool, Python Tutor. I'm sure Prof has shown you before. Let's see. Yeah, so if you guys are having trouble like with some tough tracing questions, you can use this. You'll basically trace through the code and you'll see how the values of each variable changes, like I, the looping variable, and the result, how it changes as we iterate through the while loop. But during the exam, you won't have access to Python Tutor, obviously. So this is how I usually do it. Especially when the questions get like more complicated. Okay, for this, I'll usually like to draw a table to keep track of the values of the variables. So like I and 0. So I starts out at 0, the looping variable, and the result. So this while loop will start from 0, right? And it will keep looping while I is less than 10. So first, I will be incremented by 1. So when I is 0, result is incremented by 0, then I is incremented by 1. In the next loop, I will keep getting incremented and result will be added by I. Yeah, and when I reaches 10, the while loop condition has been fulfilled. So the while loop terminates and we will return the current value of result, which is 45. All right, for full 2, Jonas Chen.
Yes. Hi.
Okay, what is the output to this part?
The photo will print 3.
Yes. So yeah, basically, for the while loop, you'll keep iterating until you reach this line of code. If I equals to 3, it'll break. So the break keyword stops the iteration of the while loop, and you end up returning the result as is. So yeah, here. So I will only be incremented until 3, and once it hits the if statement, the break keyword will exit the loop. Now, bar 1. Let's get Jeremy Neo. Hi, Jeremy, are you there?
Yeah. I got 45.
All right. Okay, so can you explain?
Uh, it's a it's range 10, then range 10 means that 10 is exclusive, but 0 is included, then step is 1. So it's same as the part A.
Yep, thanks. So, yep, it works the same way as part A. So this is just a for loop, while part A is a while loop. In these two cases, it works the same way. You iterate from I equals to 0. Because range, when you only give it one number, it defaults to starting at 0. And it ends at 10 exclusive. So it goes up until 9. So you iterate from I equals 0 to I equals to 9, and you add the result, the value of I. All right. For bar 2, what is the answer to bar 2? Let's get Olivia Cole.
Hello, can you hear me?
Hello.
Hello. Can
Yep.
you hear me?
Yep.
Can. Okay, can. So for bar 2, it's essentially roughly the same as bar 1, except there are a few exceptions here and there involving the modulus function. So there are there's a if condition here, like say if then modulus 3 equals to 1. Essentially it omits 3 different values, which is 1, 4, and 7. And the rest would carry on as per usual lah. Yeah. So for the result, we just have to subtract the additions of these 3 numbers away from it to get the sum. Yeah.
Right. So what's the output?
My output 33. Yeah.
Yep, correct. Thanks. So yep. You're right about that. Okay, so here's the table that you might draw in exam. So this is how the values of result will change. So crucially, at I equals to 1, 4, and 7, basically when it's divisible by 3, you'll continue. And that's what the continue keyword does is it skips to the next iteration of the for loop. So whatever is below the continue keyword, if it's ran, any code that's below the continue keyword within the for loop will not be ran. It will be skipped to the next iteration of the for loop. All right, so I have a few extra questions for you guys. So they are on variable scoping. So I'll give you like a minute to look through each question. And pretend you're in an exam, so don't just run the code. Just get out a pen and paper or something and like just trace through the code. And later I'll ask you guys like what will be the expected output of running each expression. No, this second question was not shown in yesterday's tutorial. I just added in today. I'll give you guys another minute. Later we'll go through these two questions. So does anybody want to volunteer for the first question? You can just open your mic and start talking. Now I'll choose somebody random. Okay, Callum Chan Jun Lao. Can you try this question?
Can you hear me? Sorry.
Yes.
I got x equals 11 and y equals 6.
Right. Can you say what the output will be if I were to run these lines? Like if I run all these lines, if I click this, what will I see in the terminal?
Oh, wait, I haven't tried that part yet.
How about you?
Oh, wait,
get
no, sorry.
just do it now?
Okay. Yeah, I'll do it now. Oh, I get 11, 5, and 10.
Yes. Okay. Can you explain your thought process or how you
yeah,
trace
actually,
through the question?
I think I get it now. So x and y are the global variables, and then it says there the call function is print extra 1, 6. So that means in the local variable x is 6. So y equals x, which means that local y equals 6, and then you have 6 plus 5. So local x is 11. And then so if you print the extra 6, you get 11. And then if you print x, that would refer to the global x actually. So that'll give you 5. And then print y would also refer to the global y, which is 10.
Yes, very good.
Yeah.
That is the correct answer. So what you do in an exam is first you should keep track of the global variables. So these are global. And now for the running execution steps. So like we'll run these 3 steps, right? So when we run print extra 1, 6, extra 1 within the local scope of extra 1, y will be set to the input x. So this is the input x, which is this. 6 will be passed in to extra 1 as its input. So within extra 1, within the local scope of extra 1, y will be set to x, which is 6. And the input x was 6, right? Yeah. Then when this line runs, x is set to the current value of y plus 5. So what is the current value of y? You take it from the inner scope, from the current local scope of extra 1. So then x will be overridden to be 6 plus 5 equals 11. So this 11 is what will be passed here. And when you run this, you'll get return 11. So this line returns 11. Over here, when we run print x and print y, we are looking at the global scope. So these values of y will be passed in. That's why you get 5 and 10 for x and y. So running the function does not change the value of x and y in the global scope unless you very specifically use the global keyword. All right, for the second question, anybody want to volunteer? You can just start speaking.
Hi, I'll volunteer.
Hi. Okay, so can you trace through your thought process or like?
Okay, so first is to take note of the global variables. So for the global variable x, it's assigned the value of 1. The global variable of y is assigned the value of 2. So firstly, the function a is run with an input of 5. So tracing through function a, x, the input parameter is initially set to 5. So when the print x function is run, 5 will be printed out. Next is print y. Since there is no local y variable created, it will take from the global scope, which is y equal to 2. Okay.
Right.
Next is is next will be the inner B function is called with an input of 3. So inside the B function, C function is also defined with an input of 7 with its own inner local x set to 7. So C inside function C print x will output 7. Then print y. This variable y is taken from one level up, which is the B function y input parameter, so which is 3. And that's all for the A function. So next print x will be the global x. So x equal 1 will be printed out. Then y will be the global y. So y will be printed out as 2.
Right, okay, let's see. 5, 2, 7, 3, 1, 2. Yes, okay, that's correct. So very good. That is exactly how you should be tracing through these kind of questions. Okay, in the exam, these kind of questions can actually come out. So basically, you'll have some questions where like you are expected to trace through, and you won't have access to a Python interpreter, obviously, or Python tutor. So you need to understand how to trace through these questions. So this question specifically tests on variable scope, your global scope and your function scopes. So you need to know that like within each function, if a line is run where you need to find like the value of a variable, like for example, this line print x, when you want to find the value of x, you look outwards. First, you start in the local scope. So you see within the scope of C, is there a value of x? Yes, there is an input variable x. So whatever was input to C will be its value of x that it knows. But let's say it doesn't, this is not here. Let's say you cannot find a value of x within the local scope of C, it will look outwards and see whether you can find it within the local scope of B. So like over here, you have your print y. You run your print y over here. Like you cannot find a value of y defined within the local scope of C, so you look outwards to the local scope of B. So you look out and you notice you have y equals to 3, which is from the input to B. And if let's say B didn't have it, it will look out to A and see whether you can find a value in A. And if not, it will lastly look in the global scope. So if you cannot find the global scope, it will probably raise an error. All right, I have one more question. This is a tricky question. I'll give you guys like a minute to see through. This is just like testing the peculiarities of Python and how its for loops work. Give you guys a minute. All right, let's get back to it. Okay, so Ray Yang So, I'll ask you, what is the output? Hi, Rayang, are you there? Okay, it's fine. His mic is not working, so we'll ask Jonas Chen. Can you try this question?
Hi, can you hear me?
Yes.
I think the print extra to result in output 400.
All right, okay. Can you trace through your thought process as to why?
Because for I in range of 100 to 103, so that means your like so-called quote-unquote index is like from 101 to 102, so 3. So then I will start with 100 plus 100 to get 200, then 200 plus 100 to get 300, then 300 plus 100 to get 400.
All right, let's see. No, the output is actually 202. Okay. Does anybody who understand how to do this question want to explain the thought process? All right, okay, so I'll go through it. So this is just a tricky question on how the range function actually works. So here you notice that you define the I here, but the looping variable within your range, for I in range is actually I also. And within the for loop, you actually update the value of I as well. So let's see. Okay, so this range function in range I to I plus 3, it will go from I equals to 100 to I plus 3 exclusive. So it will iterate from I goes to 100, I goes to 101, and I goes to 102. So first off, we start off at I equals to 100. Oh, yeah. So this line is run. So we start the for loop. Start the for loop during the first iteration, because this is the looping variable, right? I will be overridden to become 100. So I is overridden to become 100 again. Then I will be updated plus equals to 100. I will then become 200. Okay, then we move on to the next iteration, to the second iteration, where I would then be reset to 101. So I is overridden and becomes 101. Then you'll run the code inside the loop plus 100 equals 201. Then that's the end of that iteration. In the last iteration, I goes to 102. So this will override it again. I will be set to 102. And then you run this line one more time. Plus 100, you get 202. So this is basically just how Python decides to handle its for loop. So this is what happens when the looping variable, the control variable that decides this, is the same as another variable that's outside. So typically you will not want to do this. This is just bad coding practice. Usually you want to keep track of your result. So you maybe have a looping variable, but you also have a result. And what the function will do is it calculates the result and doesn't do it to the looping variable. Right, okay, let's move on to question 4. So write a function, sum even factorials, that finds the sum of the factorials of the even numbers that are less than or equals to n, where n is more than or equals to 0. Can I see your answers? Just paste them in the chat. Right, Callum, can you explain your answer?
So sorry, let me go back to my code. So I defined some even factorials for n, and then I didn't know how to do it recursively, so I did it iteratively. So I put for I in range, so start stop step. So start at 0, then you want to step every n plus 1. Sorry, you stop at n plus 1 because you actually want to stop at n, right? So then after that you step by 2 because you want to find the even numbers only. Then after that total equals total plus factorial. That will add up all the even factorials. Then yeah, that's it.
Right, thank you. So let's see. Yep, this works. So this applies the step way for the range function. You guys need to understand like how the inputs to the range work. So the start, the end exclusive, and the step. So you need to understand how the step works. So this just iterates through this range in steps of 2. So like from 0 to 2 to 4. So it only keeps the even i's. So it passes in the even i's to the factorial function. So you only increment the total by factorial with even i's. Okay, let's see for Leon. Okay, Leon did it a different way. So Leon, can you explain your method?
Okay, so what I did was first I put an if statement there. If n is 0, so it returns 1. Then second, else if it is an even number. Then if it's 0, then okay, it's basically the same as the top. But otherwise, if it's an even number, then it should return the factorial of that number. So then there needs to be another function that defines factorial at the bottom. But after it gets the factorial of that number, then it's gonna go through the recursion to minus 2 of that to take n minus 2 so that you get the factorial of all the non-negative even numbers. But then if the n on its own in the first place is an odd number, then what I'll do is it will go to the else statement, then it will return factorial n minus 1 so that it becomes an even factorial. Then it will do a recursion to reduce n by 2, and then it will continue to get all the non-negative even numbers so that to go through the factorial function.
Yep, thank you. So yeah, you can go through, you can do this problem, you can solve it recursively or iteratively. So this is one way of doing it iteratively. And this is a recursive solution, though like this if else statement inside each of the ellipse is actually unnecessary, because like if you reach this point and you like if this condition were to be true, right? If n were to be equal to 0, then it would have been caught here. So yeah, this would never run. This if statement would never be true. Wait, it will be true, but it will never be evaluated here because it would have been caught here. Yeah, so this is unnecessary. And you get rid of the else and you push this up. Same goes for here. Like if you had gone through this if, elif, and else, right, and you reach the else, I guess you can put it up here. So like so your elif n equals to 1. So you don't have to nest your if else's. Ideally, you don't go more than one level. It's just for readability. So this should work the same way. Yeah, this works also. And it's more readable. Alternatively, you can like push it up here. So if n equals to 0 or n equals to 1, return 1. Because the factorial of 0 is 1. And if you reach n equals to 1, you want to skip to n equals to 0 anyway, so you return 1 in that case also. So this is the recursive way. Yeah. You guys need to understand how to do it both ways actually, because like during the exam, like prof might ask you to do it one way or the other. So for all these questions, if there is an alternative way to do it iteratively or recursively, you need to understand both. Let's see. All right, Leon, can you talk about the time and space complexity of your solution?
I think the time complexity is O(n) squared, and the space complexity is O(n) because of the recursion.
All right, can you explain?
For time complexity wise, cause I have two recursions going on. First of all is the sum even factorials within either the LE statement or the L statement. So that will already contribute to O(n). And then factorial on its own, the definition of factorial here, I mean the function here is not defined here, but the actual function would have another recursion altogether. So both of these recursions would end up with a O(n) squared. And then for space complexity, so for input n, the longest deferred operation would be like O, how to explain this? So because of the recursion, so the longest the maximum recursion that would be like O(n). Yeah, if that makes sense.
Yep, that's correct. So in an exam, what you need to do is first you get the correct time complexity. And for the explanation for this case, is because you look at factorial. Factorial is a simple recursive function. It has a time complexity of O(n) because it has n recursive calls to itself. And for some even factorials, it will recursively call itself n divided by 2 times max. So n divided by 2 simplifies to n. So n calls to O(n) complexity function times together. Overall time complexity is O(n) squared. For space complexity, the space complexity of the factorial function is O(n) because of the n recursive calls. The maximum size of the recursive call stack will be n. But over here, right, even though in some even factorials, you call some even factorial recursively n divided by 2 times, like every time it calls factorial, it will evaluate it fully first. And the recursive call stack will hold on to like n calls max. Then once it evaluates that, it will free up the recursive call stack, it will free up the memory. So the maximum overall size of the recursive call stack for this entire run will be n. Like you never hold on to more than n variables at a time. So I'll illustrate this using Python Tutor. Oh, we need to get the call. All right, let's go for here. So as you can see, as you run the code, factorial is being called itself recursively, right? But look at this. This is the maximum size, right? N equals to 6 because the input is 6 and the maximum size of the recursive call stack, it scales together with 6. So factorial has 6 calls. Once we reach the base case, it will collapse in on itself, right? Because we have calculated the value we needed already, 720. And this continues. Notice that once we have calculated factorial 6, right? We have freed up all the calls in the call stack, you see? At first, Python had to keep track of all these values, right? But it first evaluates factorial 6, then it frees up the memory. Yeah, and notice you also need to keep track of like n divided by 2 calls to some even factorials, but when you add it all together, it scales linearly together with 6, the input size. So that is why space complexity is O(n). Now for Callum, can you explain the time and space complexity of your iterative solution?
The time complexity is also O(n) squared. Because it runs about n over 2 iterations, so that part I think is O(n), if that's the correct way I'm thinking about it. And then after that, wait, actually, oh yeah, sorry, okay, yeah, so O plus 2 plus 0 plus 2 plus 4 plus n will give you roughly that will give you a time complexity of O(n) squared, right? I think
Yep.
because you're doing factorial 0 plus factorial 2 plus factorial 4 all the way to factorial n. So I think that gives you O(n) squared, yeah. And then for space complexity, it's just it's just 1 because there's no recursion, and yeah, so it does not accumulate also. Each factorial call uses temporary memory. I think
All right. Okay,
I don't
so
know if that's a good way to put it, yeah, but does not accumulate. So yeah.
okay, for this question actually is O(n), but that's because the
Oh,
factorial we use, right, is the recursive way. So you need to look back to your helper functions. If you use any helper functions, you need to write here. Actually, I don't think our answer came with any factorial. But if let's say you did use a factorial function that had space O1, then over here, it could have a space complexity of O1. But you see right over here, factorial itself has a space complexity of O(n), right? Because it's a simple recursive function that has n recursive calls to itself. So over here, it's the same explanation. You loop n divided by 2 times, but the space is freed up every time factorial I is calculated. So the maximum size of the recursive call size is O(n), which is why this way is O(n) here. But yeah, your explanation for time complexity is correct. So in your exam, if you have an iterative function, so the way you explain it is you have a for loop that runs n divided by 2 times. So that number scales with the input, right? As the input gets larger, the more times the for loop runs, more iterations. So that's why this n number of iterations, and at each iteration, you run a step that takes O(n) time. Because your recursive factorial takes O(n) time. You run it O(n) times. So overall is O(n) squared. Now it would be different if let's say you had a iterative factorial. So let's say you define factorial iteratively. So define factorial n for n is more than or equals to 0. Just showing an example. Oh, this is not updating, right? Okay, I'm getting about, but let's say you had the iterative version of factorial and you defined it correctly, right? So it will run with time complexity O(n) and space complexity O1 because it has no recursive calls, right? And it uses a constant number of variables. Then in that case, this could be O1 if your sum even factorial uses a helper function that has space O1. Right, we can move on to question 5. Okay, question 5, what happens when we purposely ask the interpreter to evaluate the combination FF? All right, can I have Nathan? Right, Nathan, what will happen if we were to run this?
Hello.
Hello. Hi.
Yes. So if you were to run FF as in like F, you call F within F, right?
Yeah. If you were to run this line of code.
Does it? Hold on. I'm not very sure. Wait.
All right, it's okay. Let's get Yu Hang Zhou. Can you try what happens when we run FF?
Sorry, can you hear me? Right?
Yep.
I think that the outer function call will then inside F, it will run F2. Then in that secondary function call, they'll try to run 2 as a function, which leads to an error.
Yep, that's correct. So basically, you get error. Specifically, it's a type error, but you don't really have to understand exactly. But you just need to know that it's a error that comes out. So you see, FF, when we run it, all right, FF, F is being passed into F as the input, right? So within F, the G is F itself. So over here, you return F2. So F2, 2 is being input to F. Where we are at F2, 2 being input to F as G. So this will be 2, 2. Now Python will try to evaluate 2, 2, but in Python, there is no like definition on integer taking this brackets. Because in Python, right, this brackets means you're trying to call it a function, right? This is the only way you use object over here and brackets and input here. So this will mean you want to call it with input, but this being a simple integer has no definition on how to take any inputs, which is why you get a type error. All right. So I came to the end of the tutorial. You guys are free to leave. If you have any questions, I'll stay back for a while to answer. All right, bye guys. All right, so why does the factorial function being recursive or iterative affect the space complexity? All right. So here, if we had a different factorial function, I'll show a simple one over here. This one uses a for loop. So first you look at the space for this factorial function. So it keeps one variable and then it looks through and updates that variable. So the space for this is O1. Over here, O1 space. Now the sum even factorial function loops through n divided by 2 times and it adds factorial I. But because the factorial it uses here is the iterative version, right? The iterative version in O1 space. Then over here, this function itself doesn't use more than constant space. Overall, the space complexity for the iterative version is O1. Yes, you can ask about the fit function, Darius. How do you figure out the value of k for Phipps' big O expression? OK to the power of n. It's the number of calls within the same line. So like the reason why that implementation of Phipps has time complexity O to the power n is because it recursively calls itself twice at each call, at each line. it calls itself twice. So it splits off into a tree-like structure. So let's see. We have fib n, and let's say it's 5. So it will split off into fib. I'll just call this f. So f4 and f3. I'll just use balls to represent them now. So like 3, it'll split off into that. And 2, split off into 2, split off into 1, which is the base case. Then this is 1, 0. So if you look at this, you can see that over here, from f4 to f5, you basically double in size. So if you have a fib6, like over here, if you go up, if you call fib6, you basically will call here f4. So f4, you know, is the same size as this thing. So for each time you increase n by 1, when n increases by 1, when it goes up by 1, the time taken doubles. So from this tree structure, you can see that the number of steps will roughly double. So is it always true if a recursive function calls itself k times the big O will be k to the power of n? Now it can actually get more complicated than that. So generally, if you have that simple naive structure as fib n, like that, if it's written like that, it will be 2 to the power of n. Generally. So I can assume it's correct. It depends if how complicated Prof writes his functions, because it's possible that, let's say you introduce some condition that if something is true, you skip and it takes a constant time, then like this whole thing gets cut off or something. Generally, you need to read the function and like visualize how the calls work, like this tree structure. The reason why the time complexity for the fib naive implementation is exponential is because of this tree structure that it will run into. But generally, yes, if you have a line that says like return fib n-1 plus fib, the same call, or it doesn't have the return, it can have like a step. If it has one step where it calls itself recursively twice in the same line, then it will split off into 2 tree-like structures, right? Then that's why it will become exponential. All right, lists and matrices. Let's say you have a list in a list. We make a copy of that. If it's not copy in the list, it will be still the same objects. You're asking about the difference between a soft deep copy and shallow copy, yes. All right, so a matrix. If you use matrix.copy, matrix.copy returns a shallow copy of the matrix. So as the references inside will be the same. So like, if you use matrix.copy, list will then get that. But the references inside will point to the same inner list. So instead, if you want to make a deep copy where everything is copied, you need to use a recursive way, like how Prof showed in his lectures, or you just call like deep copy, a deep copy function. But I think in exam you should understand how to do it the recursive way. For that, I think it depends on Prof. But you anyhow he does teach us how to make a copy of a nested list of a matrix or like any n-dimensional matrix. Like I believe he shows the function in the exam, in the lectures, where you look through a n-dimensional matrix like recursively. So no matter how many levels it has, you can deep copy it, or you can apply any function to it. You can map over it, you can filter over it, you can count the leaves. If you reach that lecture, yeah, he does go through it. So you should know how to write it.
Okay. I wasn't following very much. Why was it deep copy come into picture? We will talk about that in one of the presentation near the end. So anytime anything about unclear in the assessment, that means in the midterm or in a final, you can always make the assumptions and state it in your answer, and we will take that into consideration when marking. That is to protect yourself. On the other hand, we also protect ourselves that whatever we said, we make sure that there is a second opinion, someone else check through the paper before we administer it. So you can be assured you don't have to worry too much about whether it's deep or shadow copying. We will make clear in our question. Anything that is our fault, not clear in our question, you can always challenge. All our answers are published after the assessment. You can always make all our answers, so you can always make contest our answers in all the forum and so on. So you are very much protected. The midterm paper will be written to you, but not the final exam paper. But on the other hand, final exam, the solution will also be given and you can contest if you need it. All right, so nothing to worry about. And just another, a little bit about Fibonacci. Just now I saw Junjie mention about the 2 to the n. 2 to the n is for the Tower Hanoi solution, is exactly 2 to the n. For Fibonacci is slightly less than that. It's 1.61, 1.6 something. Let me see, 1.618. So a little bit less than 2 to the n, because as what Junjie has drawn for you, the certain part is missing, a little bit lopsided, but still it is exponential with the base of close to more than 1, but less than 2. Still, so this is exponential, and this is indeed not what we can handle when n is large. Okay, to get to that, you need to be able to solve some of these more advanced combinatoric questions. It's not part of our course. You can always Google to see. You just go to the Wikipedia page about Fibonacci number. You will see that golden ratio raised to the power of n, which is 1.618 raised to the power n. Okay. Yeah, back to you.
Right, if there's no other questions, I think we can end the tutorial here.
Well, Junji, you can stop the recording and say goodbye. I think they're only left with 3. Bye-bye.
Bye.